Okay, hi everyone, and thank you for coming along. Really exciting from my perspective because there's wondering. Really exciting from my perspective. I'm sure a lot of you have been seeing this massive white building that's been erected on campus over the last couple of years, and this is our very first event at the JCU Ideas Lab. So thanks very much for being a part of that. And we're really excited to be holding this event with you guys. So a little bit of housekeeping. There's hand sanitizer at the front in case you missed it. There's also a sign-in register over there. So if you haven't marked your name at the beginning of the session, make sure on your way out you do mark it just for our COVID tracking and WH&S stuff. Seat placement, you guys have all done excellent, but just stay where the signs say, again, for the COVID placement, just so we do proper social distancing. Okay, so let's get started. Look, we're lucky enough, as I said, for our first event, to welcome the AWS team. So we have a couple of members with us right now. Virtually on the screen, we have David Lemphers, and just over here we have Ben Duncan as well, who's going to be sitting in on the session, and also sticking around a bit afterwards as well if you want to have a little bit of a chat. So Dave, who will be doing the majority of the presentation today, is the head of technology startups at AWS. He's had an extensive career in data science and AI, has co-founded an excellent 4 AI startups, has also done applied data science at Microsoft, so done a bunch of work with them, and is currently a CTO in residence at Techstars. So he works really closely in the face between technology and what startups are doing. Ben over here is a startup solution architect. Again, previously really successful founder. I won't go too much into his bio because he's going to be having a chat this afternoon with Mark Smarsley. So we'll give him the limelight then. But without further ado, I'd love to welcome Dave to crack on with his session, which I'm really looking forward to. So thank you, Dave.
Thanks, Keith. Just doing a mic check. Everyone can hear me okay?
Yep.
Yeah, sweet. So yeah, my session today is on AI/ML in real life. Just a little bit about me. You know, I've spent the last 10 years doing AI or ML or one of those flavors in a production capacity. Before that, I started in robotics, so still did a lot of telematics and logistic regression style systems. But it wasn't until about 10 years ago at Microsoft where I got a full immersion into building ML-based systems, and it was actually working for Bing on their recommendation algorithms. And so that kind of started me on a journey of not only doing startups, but also contributing back through the US patent system and publishing patents on the things that we were building through these various startups. So had the opportunity as well with one of my startups got acquired by a company called Retail Me Not, and had the opportunity to build up a 30-person data science team across North America and Europe. And so that was an amazing experience as well. But today's session, I really just want to talk a little bit about my own personal experience, but also the experience of colleagues that I've spoken to over the last couple of years. And as recently as yesterday, I interviewed a colleague who is now at IBM working as a data scientist. And I collected all this information and put it into 4 key categories that I really want to go over today. The first one is you're getting hired. You're going to do it multiple times in your career. I've done it multiple times in my career. Each time it's different. And it's very much based on what's contemporary, in the field at that time. So when I was first doing data science, it was machine learning. Later, it became deep learning. So again, of varying degrees and changes in the industry will change the way that you approach getting hired. The other one is really focusing on the long game. I'm a huge believer in building a credible and verifiable brand. I think Ben certainly is a great example of that, right? The ability for you to type in someone's name, see what they've done, see what they've contributed to, is really important in building your career as a data scientist. The other thing is definitely moving towards projects that are challenging and exemplary. It's one of the things we always look for is like, what is that exemplary demonstration, of your passion and skill? And it doesn't always have to be something that's overly technical. It could just be something that had considerable impact for the customer. And always try and join teams that make you feel like a noob. Like, be vulnerable in your career. You'll find that joining at the very bottom of a team just helps you kind of grow. So when you leave, you're continually laddering up your skills in your career. Ideally, your goal should be that hiring managers are seeking you out. And so I definitely am a big believer in blogging, posting on LinkedIn, which is a great channel for our industry, joining an open source project, even if you're their document engineer. Again, it's just one of those things where if you start to practice it in small steps, you can start to grow and kind of incorporate that as part of your kind of day-to-day cadence. Be really passionate about the domain you work in and the tools you use, and always think, can you be doing it better, faster, or smarter? It's very tempting in our industry to get really good at a framework or a set of tools and then never change. And there's nothing worse than interviewing a data scientist who's 5 to 10 years into their career and they haven't moved off the tools that were kind of relevant 10 years ago. So kind of force yourself and invest time to always stay on top of the kind of tools and technologies, and also just be a student of the game. I think what's really fascinating, and I'll talk a little bit about it when we get to the team slide, is there's varying modalities that a data scientist career will take, and the research space develops a large amount of content that really leads the state of the art. And then also the vendors and technology providers do the same. So, definitely, again, and I'll talk about cadence, but set time aside to become schooled, in what's out there and be well versed, in those, not only algorithms, but the technologies. And then the other thing, and this is just a general engineering discipline that I picked up when I was working in the US, but embrace excellence. Data science is tedious with lots of dead ends. And so the best data scientists think big picture, and it's not just about the model, but it's about the outcomes. So really dial in your discipline and dial in your patience, because as a data scientist, you're going to need, you need both. And then give first, help others, democratize and demystify data science for your colleagues and peers. Don't intimidate people with maths. It's one of the worst aspects of our industry, unfortunately, that you'll apply for jobs that say, require PhD minimum, right? And, require these really outlandish requirements, or they'll ask for things like 15 years of experience in deep learning, and the field has really only come about in the last kind of 5 years. So don't be intimidated, but also don't intimidate other people once you become really good with data science. Be super approachable and try and share that information as much as you can. We've also got a lot of time for this session, so I want to stop at each of these phases and ask if there's any kind of burning questions that anyone has that they want some clarity. I'll also be doing like an AMA at the end, so you can also just ask me whatever you like at that point. But if everyone's good, I'll just keep going. Yep. I guess the first thing is getting hired. And I put this slide in all my sessions because you're either getting hired for the very first time or you're getting hired for the nth time in your career, but chances are you're going to do it more than once. The first bit of experience I've learned over the last decade is pick a lane. Building knowledge of a domain science and the cheat sheet of applicable algorithms and data profiles will just help you be incredibly effective and productive in your career. It's not to say that you can't generalize later or you pick up general skills as you go, but right out of the gate, be known for something and feel confident speaking about that particular domain science intelligently. It just means that not only will you pick jobs that you feel like you're in that flow state where it's not too hard and it's not too easy, you're able to do your job, learn as as you're doing it and continue to grow. So yeah, definitely focus on an area. For me, at the very start, I didn't necessarily pick it. I was always interested in text and text-based algorithms, fell into recommendation systems and then stayed in recommendation systems for the whole of my career. It doesn't mean that I can't pick up other adjunct topics, but at the core of what I know, I know recommendation systems and text algorithms pretty well. The other thing as well is go broad and deep. So, there's a number of like emerging algorithms and techniques that will happen within your domain, but there's also just domain science. And I think that's a really interesting and important part to focus on, is try and understand what, the quants and the quals who work in those industries, what do they do? So try and get sample data sets, study the data profiles, and you'll find as a data science, you spend a lot of time staring at just large walls of data. So yeah, try and work out what these data profiles are, what are the different variables, that make them up. Try and get an intuition for how they relate. Also, I find that getting case studies on companies in that domain, and the kind of data science solutions they've deployed is incredibly useful. So not only does it help you build up a catalog of use cases that you can use as a connective, kind of tool with people, so you can help explain how, artificial intelligence and machine learning relates to a particular problem space, but they tend to also tell you what algorithms they used. So I'll give you a good example. I was working on a recommendation ranking system, and we were reading a paper from Spotify on how they used inverse matrix, and again they kind of laid out everything they'd done, and we were able to kind of leapfrog off their knowledge and then use that to inform our design. So again, case studies and white papers on what other people, Airbnb, Spotify, you name it, are doing, and really understand what are the algorithms they use. Because what you want to essentially build is this data set relates to this type of algorithm, is kind of the pairings you want to build up in your intuition. So yeah, essentially pick a lane and start to specialize in a particular domain science, and then try and understand all of the algorithms that relate to that, and when do you use them. The second one is build reps. So great data scientists have incredible stamina. All the best data scientists I've worked on, again, at companies as big as Microsoft, they have incredible stamina when it comes to going through data, feature engineering, model selection, parameter tuning, deployment and operations. They really take it seriously and they don't get fatigued. So the way to do that, it's just a muscle. And most people are literal. Most of us are literal. We're not numerical by nature. So you're gonna have to build up that muscle as you go. And so, yeah, my favorite thing to do is have a sandbox environment ready. I actually on the weekend published a GitHub project with a really simple Dockerized Jupyter sandbox that you can dump some files into the data directory, start creating some notebooks. It's already got the SciPy stack, baked in, and you can start to play with pandas and start to train a model. And again, the more you do that, not only will you become comfortable playing with the different parameters and hyperparameters of both the data set and the model, but you'll also get comfortable with the discrete steps that you take. So, fitting your model, training it, going through predictions, using the different graphing, matplotlib to kind of visualize what your model is doing. And so the more you do that, the more it becomes second nature and the more comfortable you'll feel talking about that. And also just, go through Kaggle and get the data sets and the solutions that people have already done. And again, just go through it. And the more you get exposed to the way people write code, as a data scientist, again, the more comfortable you'll get. Once you've done that, get in the habit of publishing everything you can to GitHub, because ultimately that will serve as your portfolio, and it will be something that you can use to have a conversation with a potential hiring manager or a recruiter, but it's also something you can share with other data scientists, and you can kind of hack and Splunk on these things together. So it becomes a really great place, and another great habit, and it's all about habits, right? In building your career as a data scientist. And then just get used to rinsing and repeating. Just make it a part of your cadence that, you spend a little time exploring a new algorithm or reading a new blog post on Medium and trying, what they've said. And again, if you subscribe to a number of the really good data science blogs, you'll find that they generally publish a lot of their content, and make that available so you can follow along. Fast AI is great. If you haven't come across Fast AI's blog and their free training and posts, I highly recommend it. The next step is build your brand. So I talked about that credibility, and kind of public identity. I think that's really important. So first of all, think about what you love about data science. And so for me, it was text analysis. I absolutely love text analysis. And start to form a thesis, your own personal thesis on what you love about it. So for me, I used to really think, what is it that I love about text analysis? And for me, it was this idea that you could take something textual, turn it into something that a machine could understand. So, take these kind of categorical strings and turn them into continuous values that you could train a machine learning model with. And I found that really interesting. And the output was, we only as humans have about an 8-bit data input path, and so a machine has, whatever, 64 and above. So the ability of a machine to quickly look at dense corpora of data and very quickly pull out insights, is incredibly interesting to me in solving kind of question answer style problems. And so part of that thesis is start to try and put yourself where the state of the art is, and try and understand and start to predict where you think things are going to happen. So I'll give you another example. I was at, this was my time at Microsoft working as a applied data scientist in the deep learning team. At that time, the text space was really adopting deep learning, and Dr. Vec was pretty much the standard. Glove and Dr. Vec were like the emerging standards. And it became really interesting to identify what does it look like when you start to change the Dr. Vec part into text Vec, or like corporate Vec, and starting to like really play around with variations of that. And so some of that research ended up becoming foundational to my next startup. So try and think about the thing you're passionate about, what that state of the art looks like, and then try and predict where you think it's going to go. And then start sharing that out in the ether, right? Again, I'm a huge believer in not being intimidated by that. So put your voice out there, put your thoughts out there. You're going to get people who are haters and trolls. Don't worry about them, right? They're not there to like advance your career. But yeah, like start to develop that voice so that when you do go and speak to people, you've kind of gone through it a few times, in how you formulate your thoughts on that problem. And anyway, like I always think no one really knows anything about data science anyway. So go out front and have your say and kind of be fearless about it. And then lastly, build your network. So I'm a huge fan of stalking your favorite companies and data scientists and engineers. Like I don't just stalk data scientists, but I stalk engineers and open source contributors. And I will reach out to them and I will like send them a very thoughtful, considered email, and I'll have a call to action. Generally it's like, hey, I recently did this with a friend and reached out and said, hey, I've been thinking about your experience as a founder, and I'd love to understand what were some of the early challenges you faced. And we jumped on a call and I interviewed him essentially. And so I think put yourself in that position where you want to like reach out, learn from others. And you're going to get a bunch of no's, but in startups, we love no's because it means you're statistically closer to getting a yes. And also when you do find really lovely people, be respectful and thoughtful of their time, and do the work to make every interaction count. So, remember to embrace that excellence idea. And so I, even with my background and my profile, I still do an incredible amount of research on someone before I network. And I really think about what are they going to get from it, and then what can I get from it? And I lay that out really clearly. But I don't get disheartened if I, get knocked back. And that's really important because it takes time to build your career, in such a new space. But what's really important is to put a cadence in place. So break your days and your weeks into blocks. Make sure you're studying your domain, you're practicing your data science, you're reading blogs, you're becoming that student of the game. You're blogging and sharing your thoughts, you're networking with other data scientists and recruiters, and you're humble and you're vulnerable, and you're putting yourself out there, right? And really great people. That community is a wonderful community, and they'll start to embrace you, and you'll get a really nice flywheel effect happening. And so at the end of that, you will get hired, right? That's pretty, if you follow those kind of processes, you will definitely land a job as a data scientist. And I guess that's where kind of the next step happens. So one of the things that, again, in my journey, actually, before I go on, any questions on getting hired that anyone had? Nope. Sweet. So one of the things that really took me by surprise when I first started doing data science in industry was it wasn't very well structured. And so I literally joined a team and I pair programmed for about 6 months with, I wouldn't call him a data scientist. He was essentially a mathematician who worked on the team. And we did everything from first principles, like coding algebra and calculus, into code in C++. And it was incredibly confusing and wasn't very clear what we were actually doing. And we were kind of just working in a vacuum. And as we kind of, as I graduated, in my career through different roles, I started to see these three main types emerge. And so it's really important when you're going and applying for jobs that you start to get a sense for what your job role and what your team is going to look like. So there's kind of three that I like to think about. The first one is decentralized. These aren't terms of art, by the way. These are just things that I think are the way I think about it. But the decentralized model is where you're a data scientist and you're working as part of a product team. You're generally working with software engineers, product managers, marketing and sales folks. So you're in a pod, a multidisciplinary pod. And you will, or you may have specialist folks like data curators and model trainers. So that I've worked in teams where you've had those extra non-technical operators as part of the crew. These teams are great. First of all, they treat you like a special unicorn because they don't really understand data science. And they love the fact that you're able to take this large amounts of data and turn it into a meaningful signal. And really deliver those aha moments to customers. So if that's what really drives you and you love the idea of doing that, then try and find those kind of decentralized product style roles. And the example for me is pretty much all my startups have always been decentralized. AI ML teams were like embedded into the actual product feature crews. The alternate, or the opposite of that, is centralized. And so those are classic in research groups. So at Microsoft, for example, all your peers are data scientists. There's lots of them. You might have some non-data science colleagues, but in my experience, if you're working in a centralized data science function, you'll only other have data science folks, and you might have some handlers. And those handlers' job is to pretty much work with folks that you're sharing your research or you're sharing your frameworks with. And they also act as an input into the team when you're planning the types of algorithms or problems you want to solve. These teams are great because you pretty much get to crank on first principle algorithms and you get to work on abstract problems with the goal of solving these generalized problems, that can be used by lots of different consumers. And you also get to dive deep into the algorithms that power some of the most advanced experiences in the world. So again, that was very much what it was like at Microsoft. And then finally, you have these advisory roles, right? And those are the ones where you're working in a consulting practice or a pre-sales team. And actually, the data scientist I spoke to yesterday works in that capacity. So acts as a bridge between the product teams who build the products and customers that need to consume it, and acts as kind of a interpreter of sorts and a proof of concept. So you tend to be working on proof of concept style projects. These roles are great because you're compressing the standard data science life cycle into these shorter periods with lighter scope. And you get to work on a variety of projects. So lots of reps on multiple domains and algorithms, and you get paid to play with the latest AI ML goodies. So, roles like ours, like Ben and mine, AWS are very similar in those advisory roles where, we're dropping in with a customer, we're trying to understand where they're trying to go with it. We're putting together a prototype or a proof of concept and we're handing it off and then moving on to the next one. So not going very deep into any one particular domain or set of algorithms, but enough to get someone unblocked and moving. Any questions on that? No? So I'm going to spend a little bit of time on this slide because, it is one of the, it's kind of like what's your workflow and what's your process, and what you can expect on the job. So, again, like data science ultimately is all about answering questions or hunches, as you might hear them called. Not all data science projects start with the definition of like the question, the answer, the source of data, and the cost-benefit analysis. And I'm happy to talk about that, at the end of the session and kind of dig into when you're actually working in industry, how does the business decide which algorithms and which ML systems you actually build? You don't get to just go, hey, let's go build this system because it sounds cool. Like you have to build essentially a business case. But sometimes you'll just be splunking in the data and you might get handed a data set. I've been handed data sets like, I remember being handed a 200 column, 2 terabyte data set of transaction data and just being asked, what do you think we could get out of this? And so in those ones, you're trying to abstract out a particular question that could be answered from the data set. And this is where your kind of intuition for data and the experience you've had just looking at data sets will help you do that. So, and sometimes you might just be asked, can we answer this question, right? And you'll have to work out, even if there's the raw data to answer that. In all these circumstances, you're going to start with a data set. Like there's no data science job where you don't start and ultimately caretake a data set. These data sets almost always come to you in complete disarray. They're disorganized, they're messy, and ultimately they've not been refined in any way. So that's the first part, feature engineering. And what you're really looking to do is just clean that data up in such a way that when you start to feed it into an algorithm to train a model, that you actually get some good outcomes. And you would have heard this over and over again in data science, but garbage in, garbage out. So the more work you put into the feature engineering stage. So what does feature engineering look like in the wild? The first step is just classic data cleansing. Let's dedupe, let's look for empty rows and impute them if we have to. Let's normalize any continuous value columns that we want, for the purpose of our modeling. Let's also start just generally graphing it and try and look at different profiles and behaviors of the data. So try and understand, the medians and the outliers and, again, just, bucketing categorical data and just trying to get a sense for like what's in there. Depending on the size of the data as well, it's not feasible for you to actually train, or at least in the first stage, it's not feasible to do model exploration of a very large data set because the iterative timeline is quite long. So what you want to do is sample that data. And so again, knowing how the data operates, and especially when you're getting into bucketing data, knowing that you're able to bucket that data and then sample from each of those buckets is incredibly important to the rapid iterative piece early on. But yeah, ultimately you'll spend a lot of time curating that data set. And then what's going to happen is you'll end up with what's called the gold data set. And what's really important in your job, like it may not be so important when you're kind of hacking on your own, but that whole step is a pipeline in itself and it has to be made repeatable. So you have to be thinking all the while, and especially if you're working in environments like Jupyter, you have to be constantly thinking about this being run as a pipeline where the raw data from the systems is coming through that pipeline and it's getting cleansed and fixed up. And any exceptions are getting raised through an exception process, ideally to human operators who can clean and fix that data and then push it through. And you can also talk about some of the machine learning that gets applied to the data ingestion and feature engineering process. Because again, you can train models to clean and impute data from the raw source. But anyway, what's going to happen is you're going to get your gold data set. And the next stage is to really pick an algorithm. So in the old days, and when I say the old days, like back in the day, what would happen is every time you worked on a particular project, you'd either keep your scripts, or later on as Jupyter became more prevalent, you would keep your notebooks. And then what would happen is you'd pretty much just pull that data set and push it through that notebook to see what the outcome was. Today, though, with AutoML, it's not necessary. So if you take something like AWS Autopilot, you pretty much just give it your golden data set. You tell it which value you want to predict, and it will essentially explore all of these different possible solutions. And then you can either just deploy that straight into production, which again, like if you're thinking about, first time to, kind of inference as a metric, that's the quickest way to get to production. What's also great about products like Autopilot is they still give you the flexibility to go in and change and tune those models. So in the old days, AutoML was pretty much like a black box, and it just spat out a model, and you didn't know how it kind of did it. And so you either hand tune the model or you just used AutoML. And today with things like Autopilot, you can do both, which is fantastic. And so anyway, if AutoML as your first step doesn't work, so you do AutoML, the model that comes out just doesn't really meet your requirements, then you can definitely go down the traditional approach of algorithmic exploration. And again, that's more of an advanced topic, but that's essentially the path you take. I also want to just stop for 2 seconds and talk a little bit about, again, the in real life aspect of designing these systems. So traditionally what happens in school or in kind of courses, as you're developing, is everything happens inside the data science environment, typically Jupyter. And pretty much you run everything in Jupyter and you get a nice graph at the end, or you get a classification out the end. You're like, cool, my model works. In real production systems, you tend to have lots of models. So there's very rarely one model to rule them all. And so when you're working on these real life systems, you're almost always using a number of models, and you have to orchestrate them in different ways. So for example, you might have a model that takes your data, uses a classifier to take a continuous value and produce a label. So that's what I was talking about when you've actually got like a piece of feature engineering as a machine learning model early in your pipeline. And then that might feed into a traditional like logistic regression style model. So you'll what they'll call and create ensembles, or waterfalls and flows that have many models. I would argue that best practices today is to have, just like microservices, micro models. So have models that do very discrete bounded functionality, and then just string them together as you need it, rather than trying to build one big monolithic model. Not only is it really hard to maintain and manage those, but it's very hard to monitor and operate them in production. So just something to consider when you're doing that. So the next thing that happens is you've got a model that you've trained. It's a versioned model, so you're going to be keeping these models versioned as you release them to production. And now you've got to decide how essentially you deploy that. So what tends to happen is you'll deploy it as an offline model, like a batch model, or you'll essentially mainline them. So what happens there, right? You deploy your model, and then you'll either put it as part of an API and it gets called as part of that call stack, or you might actually have it as a batch process that's enriching a data source, is traditionally what happens. So data will come in, your models, your machine learning system will work, it'll start to produce those inferences, and you'll use those inferences to update a database. So you can imagine that you've got a database and you've got a column that gets populated by the machine learning. What's really important is that you handle graceful degradation. So in other words, your system should work good without your model and really well with it. It's not that it works really well with it and not at all without it. And so that's really important, because in a lot of the projects I worked on in the early days, we didn't really understand that concept. And so when we were writing to databases, we didn't have any kind of provenance system to say, when was this last updated? Does it expire? So we would, like, the machine learning, would work. It would produce some, insights into the database. It might fail for a couple of days, and those insights are still there and they're being served to customers. So you start to have to think about the, kind of life cycle of the data that you're pushing. Or we'd have these APIs that if they didn't respond within a certain amount of time, or they took a little longer than expected, there was no way for the calling API to time out. And so now you've got the customer waiting as the AI is trying to crunch and do things. So always think about these things as best efforts, right? Like, if the AI works great, if it doesn't, the system degrades gracefully and still provides a good experience for the customer. What you'll find as well is that when you're working, especially in product teams, the construction of an ML feature is actually something that goes through the normal design phase. So product managers, marketing teams, everyone gets involved to understand what it is that the AI ML is going to do. Operations gets involved, monitoring gets involved. So everyone's trying to understand if this thing doesn't do what it's meant to do or breaks or isn't producing the right recommendations anymore, how do we deal with that? And again, like we'll talk about this in the next slide, but the concept of drift is really important, right? Because you'll train a model based on a particular data set, and then over time, especially in live feed systems, that data is changing, right? So that temporal nature of the data is going to ultimately result in a model that either has become, like, the actual model coefficient, the underlying model has become so big that it's not it's not accurate anymore. And that's called drift, right? The accuracy and ability of the model starts to degrade. And so knowing at what point do you essentially take that version out, set a window, a training window, and then retrain a new model is really important to not allow too much of the time window to be part of the model. So yeah, that's that section there. Any questions on that one?
It sounds like you might be talking about it more on the next slide, but coming from an academic background and doing a lot of deep learning there, like the measure, you talked about a golden data set and cleaning it and preparing it. I'm wondering how that goes with validation, because often we're handed, a data set and everyone's competing on, and it's just about getting the best accuracy there. But as you said, like, if you're doing production and things drift and whatnot, how do you have a preferred method of, like, measuring that over time and whatnot?
Yeah, totally. And you're right, it's actually the next slide, which is my other stuff slide. So and you nailed it, right? And I wouldn't necessarily say it's just academia, but even pure data science is very much like that. So I've worked in teams where we built the models and we didn't really think about what happens when the model goes into production. So this is where ML ops is, I think, the tagline, but essentially we just call it model operations. And model operations, it's a core requirement for data science, but I'll tell you right now, it's one that is unfortunately not very well practiced. So everyone's excited to get their model out, and used, but no one's really thinking about the care and feeding of that model. So model operations really talks about version control of both the data and the model. It's monitoring the accuracy of your model, and we can talk about, like, what that looks like metrics wise. It's also iterating and improving the capability of your model. So that's not only making sure that there's a stringent review process for the data that goes into the training process, but it's also about parameter tuning and model selection. So a lot of times you'll pick an algorithm that works really well against a data set and that produces the model. But over time, better algorithms or algorithms with better parameters and hyperparameters come in. And so you have this ability to essentially take your data set, tune certain hyperparameters that are now available in a new version of the algorithm and produce a better model. So again, it's always keeping that process linked. And the other thing as well is stakeholder reporting. So it is so critical, especially if you're doing multiple projects, that you have the dashboards, and we always ran those things automatically. So we always had reporting dashboards up and ready. anytime, like my boss, the CTO, could ask, where are we at? We could simply say, go look at this Kibana dashboard. Here are all the models. Here's the versions they're at, and here's their performance in production. And also because a lot of the times when we're building a business case for this, we're having to come up with essentially the cost benefit analysis. So the business team will say, if we can produce, let's take recommendations, for example, right? So we're building a electronic mail system, and we're going to use intelligence inside that, right? Recommendations. So we've got a number of models. We're possibly A/B testing them as well to see which one wins. So, and then here's the thing, right? You have to connect a performance metric to not the accuracy performance of your model, but the actual outcome. So if our recommendation model is that we have to pull 3 products per customer, put those in the database for the nightly email, there's going to be an accuracy calculation that we have when we train the model. So we're comparing that against that and saying, how are we performing against the test train split? But the other thing you have to also test for is, like, say that's higher, right? Say we set the bar at 80%, it's always performing over 80. It's producing recommendations, and the business metric for that is conversions. How many people are clicking and buying? So if you don't link those up together, and all you go back to the business and say is, hey, we're performing over 80%, that's not really the full story, right? Because what you want to be saying is the model is performing at 80%, so we're monitoring drift, in its performance, but also conversions from these models against the baseline, which is a non-model baseline, is 5%, 7%, 18%. So what you might actually get, right, is, and this is absolutely what happens in production, is you might have a model that's performing at like above 95%, but the actual metric, the business metric, like let's say conversions, might be low, 7%. And then another model, which might be like 83%, might be performing at 20% conversion. So you've got to take that and essentially multiply it, because essentially what you're saying is it took us $100,000 to build this model. What's the ROI? The ROI is not only the performance of the model and its ability to stay above its drift level, but it's also its ability to impact that business metric. And so you'll get into these situations where you're asked to explain your model, like explainability is huge, right? What does your model do and why does it do it that way? So you should feel comfortable to explain that. And then the other thing is that you're going to have incidences, right? So this is where the model for some reason drops dramatically because for whatever reason, and this is always why you need to be monitoring essentially the accuracy of your model in production, is as soon as it falls below a particular baseline, that should be triggering exception events to the team. And what they should be doing is essentially time stamping the data stream at that point and trying to identify if the data is fundamentally changed. So what you might find is that, oh, the data we're receiving now, it's actually different. Like the range of values, for example, in a particular feature is now very different from when we first trained it. So now we have to like essentially retrain a brand new model, and we might fix a particular window of time. You might take now, and you might always decide that you always use a lagging window of now 90 days. Right. So as soon as you hit that next 90 days, you pull version 1 out, put version 2 in, you start monitoring its performance. If it starts declining even worse, put the old model back in. So you need to be able to move these models in and out of production very quickly. And then you always have to have the no model state. What happens if we get to a stage where we can't run a model? We just don't know why it's not working. What's that graceful degradation scenario where the system can still operate? So that one is normally heuristics based, right? In the product recommendation situation, there will be some governor that says if the model drops below a certain amount, go get the canned recommendations, right? And those are just generally like a heuristic based on the most frequently viewed items, as an example. So always have that fallback scenario in there. Does that answer the question?
Yeah, pretty much.
Yeah, sweet. And so yeah, like again, like one of the most important things I've learned over the last probably 5-6 years is incident communications has become so important, because if the business loses faith in the machine learning models, and I saw this at some really big companies 3 or 4 years ago, where the machine learning team just didn't keep metrics and didn't produce these reports. And when there were outages in the model, they didn't provide incident communications. And so over time, the business lost faith. And then they were like, look, I think it's just better if we run a heuristic rather than running these machine learning models. And unfortunately, that's never the right solution. In most of my experiences, heuristics don't perform as well as machine learning models, where the machine learning model is built in a really sophisticated way, where you've got the right kind of fallback algorithms, and you've got the right kind of reporting and ML ops. So that's how you can really boost the likelihood that your project does really well. And again, a lot of you folks are going to go into teams where none of this is being done. Right? Someone's going to have R and Python on their laptop, and they're going to be like working away, and they're going to produce like an Excel spreadsheet. That's going to be the state of the art at a lot of the companies you go to. So you've got to be going in there and saying, hey, can we automate? Can we put better monitoring and operations in place so we can essentially move faster and do more? Is kind of got to be the process that you take. So that's pretty much it. And, you know, I think we got about, what, 15 minutes? So yeah, this is kind of my Ask Me Anything.
Okay, I don't mind asking, do you want to just share a story of one of your startups, a really challenging ML problem that had to overcome?
Yeah, I mean, look, so the last one that I worked on was CodePilot. And so to break it into a nutshell, CodePilot went and took, we had an interface, a web-based code editor that people would go and complete coding tasks that were kind of boilerplated to a degree, right? They would go and complete those, and we would store the change sets that they built. And then we could compare that against other coders. So you can imagine a situation where we go and get a sample from someone at Facebook, Google, Amazon, Microsoft, and then someone wants to hire an engineer, and they say, hey, go complete this coding problem. And then what we used was essentially embeddings, document embeddings, to say, here's Dave, and here's Ben, and then here is someone from Microsoft and Google. And the distance between these two, Ben is definitely closer to being a Google, Microsoft level engineer, and Dave's behind Ben. So you could actually add cohorts. You could say, I want these 15 people plotted in this graph, and I want to see who's the closest, you know, or you could just say, I'm trying to decide between these two candidates. So, you know, who's most likely to perform a particular way. And what's really hard about that is that you're not dealing with a traditionally structured problem like, you know, because we understand text, you know, nouns, prefixes, all those. We understand that really well, and there's a lot of models that are trained for that. But there's very few models that understand how syntax is written. So you could go and try and build something around the parsing tree for how a model, you know, interprets that, or you can use what we ended up using was, you know, deep learning and document embedding to essentially understand those at a character level, you know, and then kind of use cosine similarity to measure distance. So that was one of those ones where at the same time, that iterative design process is very tedious, right? And you just need to kind of go, I'm going to get there eventually, but day after day, you just can't seem to get anything out of the model. And you're just like, was this the right thing to do? You know, and then you get that breakthrough and you go, oh, got it, right? But the other part that's important about CodePilot was the models were just part of the problem. We had to build the right kind of training tools. So we had to have training tools that you could go in and correct the model. So essentially use reinforcement learning, you know, and essentially feedback. And then you also want to use transfer learning too, right? To make sure that you're feed forwarding this knowledge, you know, as different models get better at understanding different types of code. So that definitely was one of the hardest, machine learning, you know, deep learning problems I've worked on. It wasn't the hardest scale problem. Absolutely the hardest scale problem I worked on was, you know, one of the top 3 banks in the US, like I said, gave us a 200-column multi-terabyte data set, this massive data set of transactions, and wanted us to essentially try and find fraudulent events. And there's 2 problems there. The first one is the data set is massive. So we had to spin up a 16-node Spark cluster that was costing about $6,000 a day to run. It was giant because you have to move out of core, you can run machine learning in just one core, it's super fast. But as soon as you move out of core, the machine learning model has to essentially distribute the coefficients, right, as part of its training, and that becomes really hard to do. So you have to move to platforms like Spark ML to do that. So that was the first problem, right? These are massive, complex engineering problems to solve. The second problem is you don't have a lot of these fraudulent events captured. So to train your model, right, because you could, let's say, for example, we have two occurrences in there, and let's say it only constitutes 1% of the data set. You could essentially just say, well, let's just say they're all working, right? And our accuracy is 99%, right? So we don't have to run machine learning. We just can say that. So you have to like really adjust for that and deal with penalties and weights and boosting to make sure that you really push the signal up of the thing that you're trying to classify for, the high value classification. And that can be really tough to do as well.
Thanks.
Right, I have a question. Yes. When you're starting a GitHub page, could you elaborate more on what type of projects you should start with? And also, when you started your GitHub page, what did you work on?
So I don't, first of all, as a general rule, I don't get too wrapped around the axle in perfecting anything. So in the early days, they were just really basic notebooks. They were actually just notebooks from other projects that I was working on at the time. So it might be, and the easiest one, which I recommend anyone to do, is go and hand code a very basic linear model, just WB plus C, right? So, and there's a really fun exercise, go out and search for it, but it's called Bert and Ernie, or it's apples and oranges. So it's just a really simple table. It's like 8 columns, right? And essentially says, you know, if it has this attribute and that attribute, it's Bert. You know, if it has this attribute, it's Ernie. And you pretty much go through that simple table. And then you hand code the function, right, that your algorithm is going to use. And it produces a very simple model for doing classification. And so I always start at the very, very basics and then slowly build up. So, you know, you might start with that, you know, as your classification algorithm. Then you might move to something like support vector machines, which are really nice and fun and simple, well established inside frameworks like sklearn. And so each time you do that, just publish that Python notebook, you know, into GitHub. And the other reason why I published that project on GitHub, the DS Lab one, is essentially you can just clone DS Lab from my repo, and you can just say clone Lemphers DS Lab into experiment B. And what happens is all of the stack, Docker Compose, Docker, the actual SciPy notebook base, everyth's there. You just go make up, and it'll bring up a full Jupyter environment that you can do just for that project. And then you can just save, you can just commit it to your GitHub. So you can have multiple repos of this same project, but what's really fun about it is then you can hand that to someone else and they can just clone yours. And they can just say, make run up, and all your notebooks, all your data will come up too. So find ways to share your stuff really easily so it's not hard for someone to just spin it up on their machine, you know, and take a look at what you did. I think that's really powerful as well. The other reason I love working inside environments like Jupyter is you can also connect to other systems. So the reason DS Lab is fun is it's a Docker Compose stack. You can add, for example, Elasticsearch. And part of your notebook could be grab some data, do some ML, push that into Elasticsearch, run a query in Elasticsearch. So you can start to expand past just the data science boundary into the app dev boundary. And again, I think that's very relevant, you know, for when you get into industry. Because the other thing as well is most teams frown on going straight to a deep learning solution. Unless you've done it many, many times before. Like what they want to see is like set a baseline for the most simplest model that you can build, get that into production and running, and then slowly get better and better as you progress through the different eras of machine learning and the different models. But you very rarely want to jump straight into a high-end black box model as your first time round, right? Because it's the explainability and the reasoning is going to be pretty low. And there's, you know, again, very complex hyperparameters to tune. So keep it really simple when you start, get that out in production, start getting data, and then start to move up and kind of improve So yeah, I always focused on really basic classification problems because I think they're super easy. They get you really comfortable with the APIs for a lot of these libraries like sklearn. So fit, transform, predict. You kind of just get used to that API, right? And you can start to substitute other algorithms in there, as you start to play around.
And do you want to share that GitHub repo link? Or
Yeah.
share it?
Yeah, I'll email it. Well, actually, yeah, that's a good point, right? I can just screen share.
Yeah, if you can email it to me as well, that I can pass it on to everybody here as well. Any contact information or any stuff that you want to share as well.
Yeah, totally. Yeah, so essentially, this is this is the project. Did that resize when I resized? Let me share that again.
Yeah, we can see it.
Okay, cool. Yeah, so essentially what it is there's a Docker Compose stack that's running a Docker file, and that Docker file is based on SciPy Notebook. But what's really cool about it is there's a requirements file that you can just update with anything you want installed inside that image, and there's also a setup.sh. If, for example, in Spacey, if you install Spacey as a pip library, you also have to run some Spacey commands to download. And NLTK is the same, right? If you want to download the stop words, you have to actually run that as a command. So this is all scaffolded, ready to go. And inside the make file, you pretty much just say make up, right? If you're not building it, if you're just using it as is, you just say make up, brings up your project. You just name the project for whatever you want. And then you've got a data directory and a notebooks directory. And I've already got a notebook in there, which just explains how to access the data directory. So it literally in a matter of seconds, you're up and running with a full Jupyter stack ready to go with all the data science frameworks ready, built in. And you can just start hacking on that. And then you can just push that to your own repo. And then you can show that to someone, hey, check out this project I've been working on. They can clone it to and run it. And as long as they have Docker and Docker Compose, it just runs. And I think, again, that portability and that speed to get into that kind of first aha moment is so critical. But again, you also want to start building in this application development capability as well. So, and yeah, if you're using DS Lab and you hit any problems, just leave an issue, and I'll happily take care of it. And the goal is that there'll be other versions of this that have like Elasticsearch, Mongo, maybe even like an Angular front end baked in. So the idea is that you can slowly build these stacks that just accelerate you through some of the kind of drudgery and infrastructure stuff.
So back with the production monitoring stuff, do you have any, have you worked with models that are doing any sort of self-reporting from the model itself in regarding certainty of labels or something like that? Or is it purely based on external heuristics from other systems?
Yeah, in my experience, essentially what happens is when the model gets, when you call predict, essentially, it's a multi-threaded call. The predict call goes off and does what it does. On the return of the value, it just gets logged. And so you're just logging the infers that come back. And then just like any other system, right, you're just monitoring the response. And most of them produce the confidence interval, the accuracy score, and you're just monitoring that accuracy score over a set of intervals. And you could use things like Kinesis, to do that, and they'll just automatically aggregate a time window and say average, accuracy or confidence for this model is sitting at 82%. The key thing is that you also have an alarm that says if we drop below a certain SLA. So let's say, for example, when we finished the model, we were at 83%, and we don't want to drop below 80 for whatever reason, right? Essentially, you want two things to happen. You want that monitoring system to be monitoring the aggregate performance. And as soon as you drop below 80, it immediately starts returning the canonical response. Because two things, right? you want a notification to go off saying, hey, something's wrong with the model, let's go dig into it. That's probably going to be a factor of drift because the data is changing now so much that it's, the model doesn't know, it's not generalized enough to understand it. But the second thing is you don't want to be returning rubbish data, and you don't want to return nothing. So always having the canonical response, is so important in these systems. Those are for online systems. For offline systems that are doing batch processing and enriching databases, less of a problem. What's important in that design is that you have expirations set on those values so that they don't, if you know that you're running every night, you only allow those, the time to live on those is like 24 hours, and they just expire out of the database. And then the application just knows if that, let's say for example, it's like a recommendation score, right? You just go, if there's no recommendation score, just don't show it on the UI, right? And default to the non-ML behavior.
Okay, any final questions? No? Okay, great. Look, can we have a round of applause for Dave, please? So look, thanks so much, Dave. It was awesome to have you as our very first speaker in the Ideas Lab. So glad you've got that mantle. We'll send you out a trophy, something to put on the wall.
Thank you.
As I said, if you want to share with me any links or anything that I can share with the group, I'm more than happy to facilitate that and send that info on to you guys. But again, thanks very much for taking the time. Really appreciate it. There's a really good group of engaged AI and machine learning budding data scientists here at JCU, and we're really passionate about trying to build that capacity up here. So really appreciate you taking the time to help us do that.
Yeah, no, my pleasure. Awesome. Thank you so much, everyone. And yeah, enjoy your day with Ben. He rocks.
Thanks, Dave. Talk to you soon.
See you, friends. Bye-bye.